Thanks very much. Okay. Pardon? Well, thank you very much for the introduction and the invitation to speak. I'm very surprised that anybody at all showed up for this talk because the title on the website was Local Global Compatibility at Primes Dividing 1. But so I guess there's pretty low expectations for this. So this is all joint with Tom Barnett-Lamb, Toby G, and Richard Taylor. So I'd like to start by recalling the local langlands correspondence. So here K over QP is a finite extension, and omega is a algebraically closed field of characteristic 0. And then the local langlands correspondence is a bijection that's denoted rec from the set of irreducible, admissible representations of GLN of K, let me just say over omega, so on omega vector spaces. And this set, I guess up to isomorphism, and this set's in bijection with the set of n-dimensional Frobenius semi-simple. I'll explain what this means in a second. Vedolin representations over omega. And I should say this bijection depends on the choice of square root of the cardinality of the residue field. So let me just explain briefly what is a Vedolin representation. Well, it's a triple VRN where V is a vector space over omega, finite dimension. R is a representation of the Weil group of K on V with open kernel. So that just means that inertia acts through a finite quotient. And N is an endomorphism of V. And the relation satisfied by R and N is that when I conjugate N by R of sigma, this is equal to the valuation of the element of K I get by applying the inverse Artin map to sigma, and then multiplying that by N. So this relation implies that N is a nilpotent matrix. And we say that a Vedolin representation is Frobenius semi-simple if R is, and I guess the terminology comes from the fact that the restriction of R to inertia is always semi-simple, and somehow R will be semi-simple if and only if the image of some Frobenius lift is semi-simple. And we can always define the semi-simplification of R, but we can always define it in such a way that it acts on the original space V. Essentially, you just take some Frobenius lift and get rid of its unipotent part. And then we can define, given any Vedolin representation VRN, we can define its Frobenius semi-simplification to be the following. We just replace R by its semi-simplification. And we can also define its, what I call it, semi-simplification, which is going to be V R semi-simplified, and then just taking n equal to 0. So now let me talk a little bit about global langlands. So this is about associating Galois representations to automorphic forms. So I want to introduce the class of automorphic forms we're going to look at. So F is going to be a CM, imaginary CM, or totally real number field. And F plus is going to be its totally real subfield. And pi is going to be a cuspidal automorphic representation of GLN of the Adels of F. And to associate Galois representations to pi, we're going to need to impose some more conditions. So we're going to need two more conditions. So the first is that pi is polarizable, and the second is that pi is regular algebraic. So I'll explain these conditions. So what does it mean to say it's polarizable? Well, it means that there exists a Hecke character chi on the totally real field such that pi composed with complex conjugation is isomorphic to its contragradient twisted by this Hecke character. So if we're in the totally real case, we can just ignore the composing with complex conjugation. And we have that pi is essentially self-dual, and in the CM case, it's essentially conjugate self-dual. And then the condition that's regular algebraic, this is just a condition at infinity. Oh, and I guess for this Hecke character, I also want to assume that chi of complex conjugation is independent of v dividing infinity. So this condition about being regular algebraic, so as again, it's a condition at infinity. So if v is a place dividing infinity, the infinitesimal character of pi v, so this is a character from the center of the universal enveloping algebra to C. And such characters were parameterized by Harishchandra, and they correspond to elements of, so we have characters in the torus, diagonal torus. Tensored up to C modulo the symmetric group. And so I'm going to denote the, so we're going to denote the infinitesimal character by HC of pi v, which we can think of as living in here. So we just have basically a collection of n complex numbers up to permutation. And then we say that pi is regular algebraic if if it's infinitesimal, well, for all v dividing infinity, the infinitesimal character of pi v is equal to the infinitesimal character of some irreducible algebraic representation of GLN. And stated in more down-to-earth fashion, this will be of the following form. So it's just given by some n-tuple of integers. Let me say a v1 up to a vn plus a half sum of the positive roots. So plus n minus 1 over 2, n minus 3 over 2, 1 minus n over 2. And we may as well assume that these numbers are non-increasing, whatever the appropriate word is to put in here. Okay, and actually, we're going to need in this talk a couple of notions that are strictly stronger than regular algebraic. So let me just introduce these now. So sort of some more regularity conditions. Okay, so let's suppose pi is regular algebraic. Then we're going to say pi is Shin regular. This is previously known as slightly regular. It's Shin regular if either n is odd or there exists some v dividing infinity and an odd number I such that avi is strictly bigger than avi plus 1. And the other condition we'll need is something called extremely regular. If there exists v dividing infinity such that whenever we have two subsets h and h prime of the following set of integers, so we're going to take av1 plus n minus 1, av2 plus n minus 2, all the way down to avn. So whenever we have two subsets of this set of n integers with, first of all, the cardinality of h being the cardinality of h prime, and second of all, the sum over all elements of h being equal to the sum over all elements of h prime, then necessarily h equals h prime. So these two conditions will appear later in the talk. Okay, so I want to now talk about Galois representations. So, theorem. So the following theorem is due to many people. So given pi polarizable and regular algebraic, and an isomorphism I from C to QL bar, there exists a continuous semi-simple representation R, L, I, pi from GF, the Gauss group of F, to GLN QL bar, such that the following hold. So the first property is going to just reflect the fact that the pi we started with had some self-duality condition. So we have the following. If I got that correct. So that here, epsilon sub L is the L-adic cyclotomic character. The second is a weak form of compatibility with the local Langlands correspondence that I mentioned at the beginning. So it says that for all primes V not dividing L of F, we have an isomorphism. So first of all, I can take this Gauss representation and restrict it to a decomposition group above V, and take the associated Wedelin representation. And ideally, we'd like this to be, at least after we take Frobenius semi-simplification here, we'd like this to be isomorphic to what we get by applying local Langlands to the local component of pi at V. Well, really, we have to just make a twist here. So we need to twist by the norm to the power 1 minus n over 2. And for this to make sense, we regard this as a Wedelin representation over QL bar using this isomorphism I. But I said this is a weak form, so what condition 2 says is that this is true when we take semi-simplification. Okay, so for almost all primes, we expect both sides to be semi-simple anyway, so this is sort of giving full local global compatibility at almost all primes. But in particular, if there's a non-trivial n anywhere, it doesn't detect that. And thirdly, for V dividing L, R, L, I, pi restricted to GFV is de Rham. And I won't give the recipe, but the Hodge-Tate numbers are given explicitly by the infinitesimal characters at infinity and this isomorphism I. But these Hodge-Tate numbers will be distinct. Okay. So it should, so this, as I said, this term is due to many people. So I wrote down a list of people who all contributed. So there's work of Kotwitz and Clozel, Harris and Taylor, Morel, Shin, and Chenevier-Harris. And somehow this isn't the whole story. So there's some other desired properties of these representations that we'd like to know. So the first is that we'd like to show that they're irreducible. And this is known in certain cases. So this is known when pi x is discrete series at some finite place x. This is by work of Taylor and Yoshida. And it's also known, and this is essentially the reason for introducing this extreme regularity condition. It's known when pi is extremely regular and L lies in a set of L is an element of a set of primes of Dirichlet density 1, depending on pi. And this is a result of the same for Barnett, Lamb, G, myself, and Taylor. So that's irreducibility. Oh, sorry. Yeah, I should have said maybe n less than or equal to 3. Some maybe. Well, the next remark won't be addressed at all in this talk, but I just thought I'd mention it. We expect some sort of oddness property, and I'm not even going to say what that means, but let me just say again that this is known in many cases by work of Bellaiche and Chenevier, and also of Taylor. And always when n is equal to 2. C. So C is the main focus of this talk, which is we expect full local global compatibility. Compatibility. So I'll state this as a conjecture. I give it a name because I want to refer to it later, local global compatibility. And it says that for all primes of f, for all primes v of f, essentially the global and local correspondences are compatible with each other. Namely, that the Vedolin representation we get by restricting the Galois representation to GFV and Frobenius semi-simplifying should be isomorphic to rec of pi v twisted by norm to the 1 minus n on 2 tensored with C, or tensored with QL bar. So I'm going to, for the rest of the talk, I'm going to give this whole right-hand side a name. I'm just going to call it IL of pi v. So this is, you can think about it, this is just some new normalization of the local Langlands correspondence. So I should also remark that this makes sense. So I stated in point 3 here that the Galois representations are known to be de Riemann to places dividing L, and this means that we can associate to such restrictions a Vedolin representation by a construction of Fontaine. So there are some known cases of this. There's a whole talk on it yesterday. But let me just try to give some of the history. So this was first proved for V naught dividing L and pi x discrete series at some finite place. And this was proved by Taylor and Yoshida. It was then proved in the case V naught dividing L and pi Shin regular. And this was proved by Shin, essentially using the argument of Taylor-Yoshida. And then it was proved in general for V naught dividing L by Cariani. And this was explained in yesterday's talk by Anna. So the main theorem I want to talk about today is an extension of this local global compatibility to cases where V divides L. So the main result is that V divides L, then we have local global compatibility of the semi-simplification. So the Vedolin representation of RL pi restricted to GFV semi-simplified is isomorphic to IL pi V semi-simplified. And further, if pi is Shin regular, we have full local global compatibility. So we don't need to take semi-simplifications on both sides. Pardon? If we're discrete series at some finite place, let me think about this for a second. Yes, I think so.
Probably the reason is because
Yes.
homology.
Yes. Yeah.
So or generator or finding or
So just a remark, we prove a slightly stronger, slight refinement of this first result. So this notation appears in papers of Chenevier and Chenevier-Harris. So it's a sort of curly less than sign. And what this means is, well, first of all, it means that they have the same semi-simplification, and essentially that the monodromy operator on the left-hand side is in the Zariski closure of the conjugacy class of the monodromy operator on the right-hand side. So I just remarked that. Okay. So it seems that, so from how I've sort of recalled the history, it seems that essentially in all these cases that they only ever applied in the case where V does not divide L, and it seems that you might think that nothing at all was known when V divides L, but that's not really true. And what we use is the following starting point. So the following theorem. So what it says is, so let's suppose V divides L and assume, so first of all, either 1 pi is Shin regular or 1 prime pi x is discrete series at some finite place. And 2, we're going to assume that pi v has non-zero Iwahori invariance. Okay, so this is the Iwahori subgroup of elements in GLN of O of Fv that reduced to an upper triangular matrix modulo V. Then sort of full local global compatibility holds at V. So this theorem this is essentially due to Taylor-Yoshida and Shin. And although it was never explicitly written down, but this is somehow immediately deducible in the discrete series case from the paper of Taylor-Yoshida, and in the Shin regular case, it's deducible by exactly their methods applied in the setting of Shin. So let me briefly say why this is true. So, well, let me just mention some of the ingredients. So the point is that the Shimura varieties in question have semi-stable reduction, and the Vedelin representation that we're interested in can be understood using the Macrane spectral sequence, or Macrane spectral sequence. And what we do is we sort of compare what's happening for this L-adic representation with what happens at a sort of L'-adic representation, where L' is some other prime not equal to L, where we have the Rappaport-Zink spectral sequence. So here, this is for RL, and this is for RL prime. And what appears in the sort of left-hand side of the spectral sequence is cohomology of certain smooth projective varieties over the finite field, and these are the universal abelian varieties over closed Newton polygon strata. And we can use the results of Katz-Messing to compare crystalline Frobenius in the case in the L-adic case with the sort of unramified Frobenius in the L'-adic case. And technically, you need to. Katz-Messing showed that the work of Katz-Messing had a missing ingredient that was filled in by G.A. Messing. So I don't want to spend much more time on this, given that it's somehow already known. And what I want to explain now is.
Do you need to use this inequality in order to get the?
Pardon?
You need to use this inequality to get to reduce it from.
You mean this inequality?
No, the inequality on n. This remark. Does that play a role? This remark yes.
So what's?
Does that play any role in this proof?
No. So what? I'll explain later where this comes from.
I know where that comes from.
Okay. Yeah.
I'm just imagining that there's some dimension argument.
No. So somehow the monodromy operator is explicitly given in terms of the spectral sequence. So somehow in both cases you show that the spectral sequences degenerate off the diagonal, and the same argument that gave purity here gives purity here. Okay. Doing for time. So our main technical result is the following. Actually, I think I want to give this theorem over here a name. Theorem A. And then we have theorem B. So again, we're going to let V be a place dividing L. And we're going to assume that pi is Shin regular and extremely regular. And then the conclusion is that local global compatibility up to semi-simplification holds at V. Pardon? I just want to do this for the moment. It is also true, but if I remove the SS, but that's an extra step. So actually, let me just assume this for the moment, and then come back to it, and let me explain now how to finish the rest of the proof using this and some other stuff. So so using theorem B to prove the main theorem. So the main idea here is to use a sort of eigenvariety argument and techniques of Chenevier, Chenevier-Harris, Bellage and Chenevier. So let's fix a pi and a V dividing L, and let's assume we want to prove this first statement. We want to prove that semi-simplification. We want to prove local global compatibility up to semi-simplification for this pi and V. And it's not hard to see that we can reduce to the case where f is a imaginary CM. We're in the case where everything is conjugate self-dual as opposed to essentially conjugate self-dual, and we can assume that f plus is bigger than q. And so the point is that there exists an eigenvariety X, which is a rigid analytic space which is interpolating systems of Hecke eigenvalues let me just say plus refinements is not, I'm not really going to get into the details here, associated to elements of the following set. So we're going to have a set of automorphic representations. So these are going to be automorphic representations pi of GLN of AF. Pi is going to be conjugate self-dual. Polarizable. It's going to have some fixed level away from L that we won't really care about. So here we have U, some open compact subgroup of GLN of the adels of F away from infinity and L. It's going to have the same supercuspidal support as pi v at V. And it's going to have Iwahori invariance at the other places of L, the other places above L. Sorry, getting a little bit squashed here. This is for W dividing L and W not equal to V or V conjugate. And a refinement is some sort of finite slope data at these places W. The weight, that's the point, yeah. So somehow things are staying fixed at V, but at the other places dividing L is where for example, the Hodge-Tate weights will be changing and so on.
But so you are making the assumption that the other primes, the Wally fixed condition is true for pi prime, I suppose.
I should have primes, for the pi I start with.
Yeah.
Yes, so yeah, okay, that's a good point. Pi W Iwahori not equal to 0. Thanks. Thank you. So this is essentially the same argument that Chenevier and Harris used to construct the Galois representations in the missing cases. And the point is that, well, essentially this is not strictly true, but it's morally true. We have two functions, T1 from the Weil group of FV to the ring of global functions on X, and T2 and T1 interpolates the trace of the of the Wedelin representation associated to pi prime V, and T2 interpolates interpolates still doesn't look good, whatever. Trace of the Wedelin representation of R, L, I, pi prime restricted to GFV. So of course it is true in this case, but it's not true in the second case, and somehow the problem is you don't have a sort of Galois representation over the eigenvariety, you just have a pseudo representation, so you have to sort of do some work to make sense of this. But I'll just mention here that this sort of uses work of Bellaiche and Chenevier and Berger and Colmez. And then the point is that these two functions agree. Go over here. I think I'll leave the main theorem on the board. And then the point is that T1 and T2 agree on all Shin regular, extremely regular classical points. And then these are Zariski dense. So this implies that T1 equals T2, which is exactly what we wanted to show. Okay. So granted theorem B, this establishes the first statement of the theorem. Okay. So actually, let me leave that there as well. So okay, so now I want to show that the first statement of the main theorem implies the second statement. So we have the following proposition. If pi is Shin regular, or pi x discrete series for some x not dividing infinity, then full local global compatibility holds at V if and only if the semi-simplified version does. And this is, so let's see, so it has a very short proof. So in Anna's talk yesterday, she introduced the notion of purity. And we're going to use that as follows. So we're going to use the following facts. So the first fact is that if V Rn and V prime R prime M prime are two Wedelin representations are both pure, and are isomorphic up to semi-simplification, then they're in fact equal up to Frobenius semi-simplification. This was maybe even used in yesterday's talk. Okay, so this is a result that's allowing us to deduce something about Frobenius semi-simplifications just from knowing the semi-simplifications. Now we use the fact that the Wedelin representations on the automorphic side are all pure. Okay, so this is equivalent to sigma pi v being tempered for all automorphisms sigma of C. And so in this case, this is due to a Shin who shows that pi v is tempered, and Clausel, who allows us to deal with the automorphisms of C. And the last fact we use is that a Vadaline representation is pure if and only if it's pure after a finite extension. Okay, so then we can use, given these three facts, we can use base change to reduce to the case where we have Ewahori invariance, and theorem A, where we get full local global compatibility, and in particular, purity on the Galois side. Okay. So this reduces us to explaining the proof of theorem B. So. So that's what I want to spend the remaining few minutes on. Okay. So proof of theorem B. So we learned, so the idea for this proof we learned from a work of Skinner, separate work of Skinner and Kissen. And we start with the following lemma, which appears in Takeshi Saito's paper on local global compatibility for modular forms. And what it says is let V Rn, V prime R prime N prime be two Vadaline representations. And let's suppose that the trace of an element sigma of the Weil group, well, trace R of sigma, oop, that's that one gone, equals the trace of R prime of sigma for all sigma living in the V group, but not in the inertia group. Then the conclusion is that the semi-simplifications of these two representations are isomorphic. In other words, the semi-simplification of R is equal to the semi-simplification of R prime. Okay, so let's fix a pi and a v dividing L as in the statement of theorem B. And let's fix some element sigma of the V group of Fv that doesn't lie in the inertia group. And then it's by this lemma of Saito, it suffices to prove that the trace of sigma acting on the Vadaline group representation of R restricted to GFV equals the trace of sigma acting on IL of pi v. Okay, and I'm going to avoid having to write out all this notation. I'm just going to let VRN be this Vadaline representation. So the basic idea is that we want to choose L over FV, a finite extension, so this is a local extension, such that the following two things hold. So first of all, we want sigma to live in the subgroup WL inside of WFV. And second of all, we want that we want to reduce the case of Iwahori invariance, so we want that the base change from FV to L of pi V has non-zero Iwahori invariance. And this just means that R restricted to the, this just means that essentially the R R prime, which is the R for IL pi V, is trivial on the inertia group at L.
Is this a different sigma to the old sigma?
This sigma is the same as this sigma. Yeah, so we want to keep, essentially we want to keep this sigma floating around, but we want to reduce to the case of Iwahori invariance. And then the fact that sigma is not in the inertia group allows us to find such an extension. So this is fine. And now what we want to choose, we want to find a global extension, E over F, is going to be a CM finite extension such that E of U is isomorphic to L for some prime U dividing V of E.
I'm sorry, maybe you said it, but what is R prime here? It's R at another prime?
R prime is the open kernel representation of the V group associated to this Vedelin representation. So
Okay.
just having Iwahori invariance corresponds to R being unramified. And then what we want to do is want to apply theorem A to the base change of the automorphic representation pi from E to F. But the problem is that this base change might not exist. So, well, E over F. So base change only exists in the case of solvable Galois extensions. So this cannot, well, may not, in general won't be, may not be Galois because L over FV, it may not be possible in some cases to choose L over FV to be Galois. So instead, we let L prime over F over FV be the normal closure of L over FV, and then and now we can choose a solvable finite CM extension F prime over F such that the completions of F prime above V are all isomorphic to this L prime. Okay, so, and then the R through close L implies that pi f prime, which is the base change of pi from f to f prime, exists. And now what we want to do is we want to descend back down again to a suitable field E. So we define E to be f prime intersect L, which we regard as a subfield of f prime W for some W dividing V. So we have the following picture. We have f down here, we have f prime up here, and then we have this sub-extension E. So this will be non-Galois in general. And then the local situation is we have fv over here, we have f prime W equals L prime, and then we'll have E completed at U equals L. And we have a pi here, and we have a pi f prime here. And now we can descend back down. And to descend back down, well, you can't always do it, but you need some irreducibility condition on the Galois representation. So we have the following theorem of Arthur Closel and Harris, which says that if RLI pi f is irreducible, pi f prime, then there exists an automorphic representation, which I'll call pi e, over gln of A of E, d dels of E, such that RLI pi e is isomorphic to RLI pi, the thing we started with over the original field restricted to GE. And now we're essentially done. We apply this theorem. So since pi f prime is extremely regular, we can find pi e. So the point was that the Galois representations associated to extremely regular automorphic representations are irreducible, at least on a density 1 set of primes. So what we have to do is we pick some other L prime where the Galois representation associated to this is known to be irreducible. Then we apply this descent result, we get down to pi e, and then we look at its L-adic Galois representation. And necessarily it will have to equal this guy. And then we're done at this point. So.